Hello boys and girls, welcome to another episode of FoulkesBrau. Today we're going to carry on with our Back to Basics building block series. We're going to expand a little bit on the emitter-follower, and we're going to add some protection to it. So we're going to learn a new building block to add to that circuit. All these building blocks are part of a bigger circuit that we're going to build at the end of the day. Well, I'm building for a colleague, but they will help you. So let's take a look at our circuit on the bench, and then we'll have a look at it on the breadboard and take some measurements with the oscilloscope and see what we see. Right, so here we are on the bench. If we forget about this part over here coming out the top, and we look here, we have our power rail through a fuse, through our first, our emitter-follower transistor, and we have a base resistor, current limiting resistor for the base here. We come down through that transistor, and the same transistor, down to our Zener diode, and we have this potential divider, voltage divider in that resistor feeding that base. Forget about that capacitor at the moment, I've just drawn that in. So what we know is when we switch the power on, that transistor will be off because there will be zero output. We will turn that transistor on, the voltage will rise, and as the voltage rises, we'll give more feedback into the base here, thereby drawing that through that Zener diode, and that Zener diode will give us a voltage reference. As this voltage rises more, that transistor will switch on harder. And the harder it switches on, the more current it will allow through that Zener. The problem is it's going to get to a point where, how would I put it, the voltage there is always going to be that Zener plus the base emitter voltage. And of course, how we calculate it in this formula here, the gain I've taken is 50, and I'll show you in the data sheets why. We've added a capacitor here, and that's I will show you on the scope why we're going to do that. But now today we're going to talk about a crowbar, which is this circuit here. So you'll notice I've got a fuse here, and you'll notice in this calculation we calculated this base resistor based on the voltage and current we want out here. So this transistor in effect is going to limit the current. That doesn't help us much, because what happens when that, or if that transistor blows, because in my experience and in general, when these semiconductors go, these transistors, they fail short. And if they fail short, that means the voltage that is here is going to be the voltage that is here. And we will destroy everything downstream. So what we can do is we can use this circuit. And we're already familiar with the Zener diode. And by just changing the placement, forget about these two resistors at the moment. If we don't worry about that, that Zener will have a voltage reference. So that means the voltage there, well, if that resistor wasn't there, would be the same voltage as that until it gets to a point, and then the Zener will start passing current. So I know from the circuit that we will be designing, we have voltage input range from 40 to 56 volts, and what I need to power downstream of this circuit has a maximum voltage rating of 40 volts. So I want this circuit to trigger less than 40 volts, and I can do it by adding these two resistors. So that's a 33 volt resistor, 5 milliamps through the Zener in this case. We can see the IZ 5 milliamps, and if we look at the resistance or the volt drop across that resistor, we take it 820 ohm, which is what that is. 5 milliamps times 820 will give me 4 volts. And we've added another resistor down here, 270 volt. And the 270 volt will give me 270 times 5 milliamp will give me 1.35 volts. So if I add the volt drop across the two resistors and the Zener together, my SCR will fire at 38.45 volts. And the SCR is a very simple device. I have to put a voltage on the gate and a little bit of current, and it will switch on. I can take that voltage away, it will stay on as long as I have the holding current. And it's very simple. If we have a look at the data sheet for the device that I'm going to use, don't care about the first page, we actually care about the second page. So if we just focus again here. So the type that I am using for this specific thing is a TIC 106D. The gate trigger current 60 microamp, very little current to trigger it. The gate trigger voltage anywhere from 0.4 to a maximum of 1, but typically 0.6 volts. So very little voltage, very little current to trigger it. The holding current that we spoke about, in other words, I've switched it on. The minimum holding current to keep it on is 5 milliamp. So I can switch it on and it will stay on as long as there's holding current. What they don't give you in this is obviously they don't give you the latching current and things like that, but we're not, I think they refer to latching current as the trigger current. Why do we want to use this? If we look at the, is it on this page? No, it's on the next page. If we look at the maximum ratings for this, sorry for bumping you there. Well, the continuous current that this thing can handle is 5 amps. But I think that would probably be pulse, so we can work on 3.2 amp. It's got quite a lot of voltage that it can handle. 400 volt across the two main terminals, if you want to call them that. So it's quite a nice device. What is very nice about this thing is that it switches on very quickly. So the rate of rise of the off state is 10 volts per microsecond, so very, very quick to switch on. Of course, that is from off. Just now the SCR is off, it's going to, when you switch it on, it's going to rise at 10 volts per microsecond, so very, very quick. Now, why do we need that? If we go back to our circuit, I'm just going to move this across because we don't care about that part of it. You'll see we've got a 12K resistor on the gate, and that is to give us that from here, that 0.6 volts at 6 microamp, I think it was. So that's what that current limiting resistor is there for. So if we look at where we're going to switch, we take that line at the top, it's coming from our supply. after the fuse. So if this voltage here goes up to about 38 volts, the Zener will be passing. It will switch the gate on. That will latch and it will pull power through the fuse to ground. In other words, it will create a dead short, a catastrophic short. And that is intended because what we want to do is we want to blow that fuse. This is in the case really if this transistor fails and fails in a short. So if it fails as a dead short, our crowbar will kick in and will pull the current through the fuse, through the top line, through the SCR to ground. Nice and simple. Of course we don't. Under normal circumstances this will not trigger. To reset it, the only way that you can reset the SCR is the voltage must cross zero. It must go back to zero, that voltage there, which will happen once the fuse is blown, so we're not worried there. Under normal circumstances this circuit will be regulating, so we don't particularly care. Interestingly enough, the transistors that I'm using there are these MPSA43 transistors, and I have two data sheets on this thing. So if we look at the first one, this one, well, we know the max ratings collector emitter voltage is 200 volts, which is more than enough because we've only got 56 volts, emitter base 6 volts, continuous current 500 milliamp. Well, at 56 volts I really only want to carry 70 milliamps, and we have to be careful of this. The power dissipation 625 milliwatts, and nothing else really interesting there. What is interesting is if we look at these figures down here, the collector emitter saturation voltage is 0.4 volts, the base emitter saturation voltage 0.9 volts, the gain 50. Now that is from Central Semiconductor. Now I have the same device, different data sheet, well, same device, different company. So this is on Semi, and what we can see there, the base emitter voltage stays the same, which is 0.9 and 0.9, the base collector emitter 0.4 and 0.4. Interestingly, this one has got a gain of 40, where the other one's got a gain of 50. So now what is the gain? It's, yeah. But anyway, we've worked on a gain of 50 for this device. One point to take note of, so the gain is 50. What we did see up here, power dissipation 1.5 watts. Now keep that in mind. I just want to come back to our regulator circuit. We've got 56 volts here. We want roughly 33.9, so 34 volts here. So that is one big volt drop. If we think of it, it's roughly what, 22 volts drop across there. So we're going to call it VQ1 is 22 volts that we are dropping, and we said we want to feed 71 milliamps, and that's typically the load that I want to drive with a bit of headroom. So let's say collector emitter equals 71 1 milliamps. Now if we want to know the power dissipated across there, we can just say P equals VI, which is going to be what, let's say 22 times 0.007, sorry, 0.07, and that's going to give us 1.54 watts of power. So if we come back to our data sheet, we are limited to 1.5 watts. So that transistor is a bit small, and I fell into the trap because I only looked at that parameter of the data sheet after I'd blown a couple of these things, and I couldn't understand why. So always take into account the power. So what I will do is that transistor up there, I will change for something that can hold more power. Now what this circuit is going to do, we can see we've got 50 to 56 volts supply. What it is a friend of mine has got a solar power system at home, so he's got a battery bank, and being South Africa and our exchange rate, he hasn't gone the full hog. He's gone with something to power just what he needs, but unfortunately it's tied into his house grid. So what he's trying to do is trying to make zones, so different circuits in the house. So for example, your geyser is on its own circuit, your stove is on its own circuit, your certain plug points will be on one circuit, another few plugs will be on a separate circuit, certain lights will be on a circuit. So by monitoring this battery level, ideally we'll do that later on, but obviously I don't want to take mains power, I want to take it off the battery bank, so that's why we got between 40 and 56 volts. I can regulate my voltage, I can create some protection for that, for overvoltage, and later on we're going to go to switching regulators and things like that. So why didn't I just go with a switching regulator here? Well, defeats the object. If we can use the building blocks, why not? A switching regulator in higher voltage is quite a bit more expensive, so we'll do the trade-off. We'll do it this way and see what power we're losing. I'm not worried about milliwatts on a huge battery bank. I mean, that's really not crucial to me, because the circuit we're designing is only going to pull 4 watts. But like I've said in the previous video, know that this thing dissipates a lot of power. I mean, we've already seen at full amperage here, we're throwing away 1.5 watts of heat gone. I mean, that resistor there, if you took the 5 milliamps at the 4K7, you're looking at about 100 and something milliwatts that you're throwing away there, and so on and so forth. Yeah, not really much, because it's just the 0.4 volts of the collector emitter voltage. So not a problem. Now, I'm going to bring the breadboard down, and we'll see why have I added that 100 nanofarad capacitor there. So let's bring the breadboard down. Let's show you the circuit that we built, and we'll discuss it further. So here is our breadboarded circuit. Don't worry too much about what's going on up here. That's the switching regulator that we're not discussing today. But basically our DC voltage from our bench power supply comes onto that rail there, over here. So that'll be our, currently sitting at 56 volts. We take that rail, we go through a fuse, and we come down to here. Here's our base emitter resistor for the pass transistor. The pass transistor is sitting in, if we can get that out the way, sitting down there. Here is the base Zener transistor, our feedback there, and the Zener to ground. So that's our regulator, so our feedback. From that emitter, it comes down to this rail down here, and all I've done is put an LED in to give us some load. And you can see my oscilloscope, I'm just probing across the positive and negative. So that 0.1 micro or 100 nano is not in here. What I'm going to do, we're going to go up to the scope. I'm just going to show you. Let's take the focus off. I'm going to put this capacitor across those rails, and you'll see why we're going to do that. A new formula that you will learn for this, the AC reactance, because remember, this transistor is switching currently, because it's got very minimal load, it is switching on and off at its rated bandwidth frequency. So it's switching on and off because it's got so minimal load. It can't control the voltage nicely, but by switching on and off we get the average voltage. Yes, no. Okay, so let's take you up to the scope and we'll take it from there. Right, so here we are on the scope. I'm just showing you where we're probing. We're actually probing, so between that point and there. So the output past the crowbar, so past the crowbar and there. And you can see what it looks like. Of course, the signal is AC coupled because I want to see what AC noise we're getting, and we can see it's at a frequency of 9.5 megahertz. Voltage peak to peak, in other words from there to there, is roughly about 4.1 volts of noise. Although, like I said, the average voltage of that is only 20 millivolts, and that we of course want to get rid of. That how would I call it, that 21 millivolts, we really don't want it to be able to go and falsely trigger our gate, even though on the gate we did put in a 100 nanofarad capacitor. So what I'm going to do, I'm going to go and put a little 100 nanofarad across the rail that I showed you early on, and watch what happens to that signal. Gone. Excellent. Only happened because that transistor had no load. So we're going to put the 100 nanofarad in our design. It doesn't hurt to take out the noise. What I'm going to do now is I'm going to plug, well, we'll take the capacitor out and we'll see. There's your noise again. We'll just turn it down a bit. You see, noise. And we'll put it back, and the noise is gone. Also, interestingly enough, no, I'm talking cuck, so don't worry about it. So let's go back down to the bench, and well, while we're at the scope, let me plug the extra load in from the switching converter. So there's the switching converter in. You can see I've just pulled the transistor out. I'm just going to set the trigger. So you can see we've got a little bit of a spike there, and it happens at, let's go increase the time base, and you can see it's happening every now and then. So I've got the capacitor out and I've only switched load in. I'll take the load out, and there you can see that fluctuation is back. So we'll put the capacitor back because we don't like it, and we'll put the load on, and let's just set the, you can see that peak is greatly diminished, which is fine. Is it worth adding more capacitance? No. What we need to do is add a bit of a filter circuit, because obviously we don't want this going back into our system. So what we're going to do is we'll go back to the bench and we'll show you how the crowbar works. Right, here we are back on the bench. We can see the LEDs on. The LEDs on. I've put a 100 milliamp time-like fuse in there. What I'm going to do is I'm going to start slowly turning the base voltage of the feedback transistor. So basically what it's going to do is push our output voltage up. Of course, this pot is very sensitive. So we're trying to turn it slowly. 34, 35, 35, 36 volts, 36.8, 37 volts, 'kay, we've run out of feedback, so 38. Of course, I've turned my supply down to try and show you the feedback, and there we go. So just under 39, you can see the LEDs went out and the fuse blew, and our output voltage has gone to 0. So you see how quickly the crowbar reacted. Of course, if I turn that feedback down and go and put in a new fuse, of course I don't have 100 milliamps lying around, so I'll just put in what I had in there. What did I do? Ah, that came out, yes. It's a balancing act today. Have I got a fuse? Let me just get a fuse and then I will put the new fuse in. Right, we're back. I have a new fuse. We'll just drop it in. And then everything comes back so we can see our crowbar worked. That little capacitor that we put in there to get rid of that horrible noise on the transistors, easy calculate the AC reactance. In other words, XL AC reactance equals 1 over 2 pi FC. So we took that resistance of the, how would we put it, if we took the frequency of that noise that was happening on the bass, which was roughly about 9.5 megahertz, times 2 times pi times 100 nanofarad. Take the reciprocal of that, you'll find that it's a couple of milliohms resistance. So this capacitor is offering a couple of milliohms to that AC noise. So all that AC noise is going through that capacitor to ground. Anyway, interesting little circuit, the crowbar. There is our voltage divider with the current limiting resistor that's going to the gate. So if you're doing a series past the emitter-follower voltage regulator like this, make sure to put your crowbar, because this thing has no protection. Of course, I'm going to have to change those transistors from the MPSA 43s to something more suitable, probably TIP or TP50 or something like that, in a TO220 package. It can handle a bit more power, and it's a lot more rugged. These two TO39 cases are not best, but I had them lying around, so that's what I used. Anyway, let's finish up, and that's it. And there you have it, boys and girls. We come to the end of another episode. Today we learned a little bit more about the emitter-follower, as well as the protection we can offer to a circuit for overvoltage, and how we can protect our series emitter-follower voltage regulator. Very simple, SCR, very nice to have a couple of them in your parts box, your bin. Keep a couple around, very, very handy. As always, I hope you had fun. I hope you learned something. This will become part of an ongoing project. Like I say, we're designing something for a friend, and of course we're trying to do it with the basic building blocks. Of course, later on we will add more fancier things to play with, but it doesn't help we go to the fancy things if you don't understand the basics. Of course, being in South Africa, with the way things are going and the way things are at the moment, if the politicians sneeze, our currency goes for a loop, and we pay a lot of money in forex to import parts, so it's not always feasible. So we have to make do with what we have. Anyway, as always, I hope you had fun. I hope you learned something useful, and we'll catch you in the next one. Cheers.